Welcome again, Betas, to a new lesson. In this video, we'll see the true power of index notation, and we'll see it by proving all these vector identities. So, this list of vector identities comes from the beloved book of physics, Introduction to Electrodynamics, by Griffiths. When I was reading that book, it kinda annoyed me that along the theory, he would just pick up one of these equations and use it, and I didn't know like the proof or where does it come from or why is it that way. So in this lesson, which is going to have maybe 3 or 4 parts, we are going to demonstrate all of these equations with index notation. Take into account that we are assumed to use a Cartesian basis because we haven't seen like how to manipulate indices when we are in other coordinates which are in flat. Let's begin with the first one. We have that the dot product of the cross product of B and C with A equals to the dot product of B with the cross product of C with A, and also the dot product of C with the cross product of A with B. So what we are going to do is that we are, for example, going to rename this as a vector D, and we are going to write in index notation the dot product between A and D, which is simply AI DI. Now, we saw in lesson 1.1.2 that if we have a vector, in this case it's D, which is a cross product of another two vectors, it's written as follows. Okay, so what we are going to do is that we are going to demonstrate, for example, this equality. We are going to arrive at this result. And for this example to work, we need to remind ourselves of the antisymmetry property of the Levi-Civita symbol. This means that if we interchange any pair of indices in the Levi-Civita symbol, it will appear a minus sign. So, for example, we have that epsilon ijk equals minus epsilon jik, but we can also interchange I and k, so another minus sign will appear and it will cancel with this one, and now we will have epsilon jki. So we are going to substitute in the epsilon ijk by epsilon jki, and we are going to move the b to the front. For example, we're in this notation, so we can move everything where we want, okay? So this is just like multiplying scalars. Okay, so what we can see now is that this is the jth component of the cross product of C with A, okay, because it has the same structure. For example, the two vectors A and B, this is the ith component of the cross product between A and B, and like this happens when we have the second index repeated with the first vector and the third index repeated with the second vector, and the free index stands in the first slot. So here we have the second index with the first vector, the third index with the second vector, and the free index here. So this is just Bj and the j component of the cross product C with A, and this is just the dot product of B with C cross A. Okay, so we have proved the middle one. We are going to move now to the last one, which is simply that I'm going to copy this. Now we can interchange, for example, the k index by the I index, And now we are going to interchange the j index by the I index. So two minus signs appear, but they cancel. And now we can write this as ck epsilon kij, and now ai bj. And now, as before, we have the second index with the first vector, the third index with the second vector, and the free index k. So this is just the kth component of the cross product of A with B, and this is just the cross product of C with A cross B. Okay, so this was the first one. Now for the second one, we have to remind ourselves a property of the epsilon, well, the Levi-Civita symbol that we saw in the last part of lesson 1.1.2, which is this one. If you contract two Levi-Civita symbols with their last indices, for example, we have contracted both of these, we'll have that this is equal to the Kronecker delta of im times the Kronecker delta of jn, okay, minus the Kronecker delta in Kronecker delta jm. So we are going to go with the second one, which is that A cross B cross C equals B times scalar product with A and C minus C times scalar product of A and B. This is a very popular vector identity, and we are going to prove it. So, first of all, let's, as before, call the cross product of B and C by D, and we see that the I component of D is just epsilon I j k of bj ck. So we are going to have that if we want to do the cross product of A and D, this time we'll have am n l, well, I'm going to write I, okay, epsilon mni, now we have an and di, okay, so this is the cross product of A with D, okay, A with D, but now we know that D is this thing, so we are going to substitute it in epsilon mni an, and now epsilon ijk bj ck. So we can reorganize all of these. We have epsilon mni, epsilon ijk, and now an, bj, and ck. So we see that we have two Levi-Civita symbols multiplying each other, and they have one index in common. They are summing, okay? The other indices are all different, but they have the both indices repeated. So we can use this property. Okay, we can write, well, first of all, if we want to use this property where these Levi-Civita symbols have repeated indices, we need that those indices, they have to be in the third slot. So for this Levi-Civita symbol, it's okay because it's in the third slot, but for this Levi-Civita symbol, it's not okay because it's in the first slot. So what we have to do is to move it to the last one. And we can do it by, for example, we can swap the j by the a, the j by the I, and we have epsilon jik, and now we are going to swap the I by the k. So we will have epsilon jki. So this is equal to epsilon mni, epsilon jki, an, bj, ck. And now we can use this property because we have the summing indices in the third slot. So we will have delta mj delta nk minus delta mk delta nj times an bj ck. Now we are going to distribute all of this. An bj ck, and now we have the other term an bj ck. So I'm going to make some space. I'm going to erase the first one. And now we have to remind that the Kronecker delta it collapses indices. So for example, here we have repeated these j's. So we can kill the j and put in the m. And the same for this other Kronecker delta. We have the k repeated with a Kronecker delta. So the Kronecker delta comes here. It erases the k and it writes in the n. So we'll have an bm cn minus and now these Kronecker deltas, the k it substitutes in the m, and for the j it substitutes in the n. So we'll have an bn and cm. Note that we have as the free index the m. Okay, so for example, we can have, let's say, this is not valid, okay, because if we have two terms that are summing with different indices, like you can't make the sum. But here we have two terms which have the same free index, and well, these are dummy indices. You can write there n, I, j, k, it doesn't matter because they are summing, and the sum isn't going to change because of the name of the index. So what we are going to do is that we can rearrange this as bm times an cn minus cm times an bn, but an bn is a dot product between the vectors a and c. So we have here a dot c, and the same for a and bn. We have the dot product of a with b. And now we see that what we have calculated here is the m component. All of this is the n component of this expression. So to make it clear, this is because this is where we come from. We come from making the double cross product from these vectors. This is the m component of this thing. So we can finish by saying that we now can transform bm and cn into vectors. So we have the vector b times this doesn't change minus the c vector, and this doesn't change. And we have proved the vector identity. So in the next video, we'll prove some of these product rules, and see you later.